What's up, guys? Welcome back to Calculus Tutorials, and today we're going to be looking at our first integral. Um, Probably, if you're new to integrals, probably don't start with this video because this is not going to be, very friendly to how to teaching you the basics of integrals. This is a very advanced, not, I don't want to say very, this is a advanced integral. Um, this is beyond calculus 1 and 2. If you are looking at this stuff, you're probably looking at it because of a result as like calc 3, or like you're taking some sort of a math major and would be mostly your first interaction with these types of integrals. Um, Not to mention, obviously, if you've noticed up here, there's a standard deviation sign. These integrals are this type of integral is mainly used with statistics, like analysis. Um, it's mostly looking at like a normal distribution and the area under the curve. With that, um, is where you're mostly gonna see stuff like this. So like, yeah, Gaussian integrals. I'll probably call it Gaussian a couple times. Laplace, because he was the dude who kind of came up with this whole thing and proved uh, a bunch of formulas and a bunch of equations relating to this integral down here, this sort of integral. At the end of the video, I'll show you like a really easy way to calculate these sorts of integrals when they're pretty much in the same form as this. Like it doesn't even require any math really; it just requires you to remember the formula to do it. So let's get started with this integral, shall we? Okay, so starting off, you might say, oh, x squared, I can just do like u substitution and make it so that it's e to the u and blah blah blah. Considering it's the only, there's nothing else here, you can't. Same thing with integration by parts, obviously, and not most, all other methods of like normal, um, elementary is what they usually say, elementary integration. So yeah, this requires a lot more knowledge and a lot more, a lot different approach. So I'm just going to start off by um, defining I as this integral from that. There. This is I. This is basically the thing that we're solving for. We are solving for I. So you might be able, if you know about multiplying integrals, which again is not a Calc 1 and 2 thing, this is above that. This is above that. So that's what I'm going to do. I'm just going to square I real quick and just square both sides. Put parentheses. And doing this will essentially allow us to rewrite this entire equation. There are some rules that go along with doing this, and they're not the most fun to work with just because of how, you know, easy it is to make a mistake and how long these problems end up taking. So I'm just going to start this next step that I'm about to do. What I'm about to do is called applying linearity to an integral, actually. So I essentially want to rewrite it in terms of x and y. Dx. I should have wrote, yeah, I'll just write dx up here and dx down here, etc. There should be dx's at every integral at this point. That'll become more important as we go through this. And then just gonna multiply real quick. Just gonna slide over. same thing, but instead of writing e to the x and writing it in terms of an x, just did what I was trying to say not to do. You want to write it in terms of y, and then write dy. So essentially, what this does is it shows that it's basically a plot of both the x and y growth. Think of it like a parametric in a way. Like x of t, like etc. It's a lot different. It's not a perfect analogy, but that's essentially what it is. It's just writing it in terms of a different form. But this is technically right as this because we squared it over here. The reason that sort of works where you can square it is really convoluted, and it's very very like advanced. It's not the yeah. You just have to, at this point, if you're like having trouble with this, it's probably just easier to acknowledge the fact that that's how that works, because that's trying to look to see why you can do this from this is a lot harder and doesn't it's beyond the scope of most courses that will introduce you to this sort of stuff. Because in terms of because when you're applying linearity and doing this sorts of math, this is a very basic, this e to the negative x squared is a very basic sort of intro to Gaussian integrals. And you'll see why later once I write out the entire equation, or the formula for finding these. So another thing about multiplying um, integrals is that we can just combine these two. Um, so I'll just put a negative outside and then do squared plus y squared, and then dx dy. You basically just ship them together because they both have the same base, they both have the same boundaries, and it turns out that their things up here, their exponents, are very close together. And what I'm about to do next is very, 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 very important to doing this sort of stuff. Now, if you know like a little bit, if you can remember what about polar coordinates and stuff like that, you got r and you got theta, and dr, d theta, etc. Stuff, you basically have this. This is your polar coordinate. This is your x and y. Now, you also have, let me put this in a different color. You can find r. You can find theta as well, but it's not as important as finding r. If you remember, r is equal to x squared plus y squared. And, yeah. Now, looking up here, it's like, what do we have up here? That's exactly what we have. Or r squared, my bad, is equal to this, not just r. So this is really where, and then you also have dx dy as well, which will, because we're trying to morph this into polar coordinates, into polar form from Cartesian, just because it makes it easier to work with and you can simplify it even further. So this is really the crux of these sorts of integrals, is being able to convert it to polar form and back to Cartesian, basically at will, and just to simplify it even further. That this is the crux. This is important. So that's exactly what I'm going to do. And another thing that you need to remember, polar coordinates, if you've looked at it like a polar graph, it's a circle and it goes from 0 to 2, well, yeah, it goes all the way around, 0 to 2 pi. So, and it'll just keep on going and have the same values. So no matter what, so basically, instead of keeping the infinities, because those don't really mean anything in polar coordinate terms, they really don't, because um, it's just going to keep on doing the same values, repeating the same values. So I'm just going to convert the I'm sorry, I just realized I should have put another integral right there. I'm so sorry. Like I did back here. There should be a double integral here. Um because you're basically you're multiplying and you need to keep the same level of integration. So what I'm gonna do is instead of writing from on one of these, because you still have to keep it bounded in your R, you can't just swap them both. So I'm just gonna change one of them, and I'm going to change the inner one to 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 0 to 2 pi instead of negative infinity to infinity. And I'm also going to change this negative infinity to 0. Um, because you don't want to have it go from it can't. Okay, so it being it being like negative in this instance is going to make it so that you can't do this problem. Um, yeah, it just can't be negative. Whenever you do these sorts of problems, you always never have a negative boundary. You have to have it be at 0 to some value. 90% of the time when you're doing these sorts of equations, it's just going to be 0 to infinity or 0 to 2 pi or something like this. So, yeah. Because otherwise it won't give you the sort of answer that we're looking for. It'll give you a very very wrong answer. And I'm pretty sure that depending on what your boundaries are and what exactly your Gaussian integral looks like, it's literally impossible to integrate. So here we go. And yeah, this is basically your this right over here. This is basically your where this if you got it this far, it's basically just the easiest thing in the world to solve. Um, so you can, if you notice, this and this are going to cancel out. Because 0 to 2 pi, this is a factor of theta. This is going, like, okay, you could plug in 2 pi and solve this integral right now, and you will get 2 pi. You could do this integral and you'll get 2 pi. This is basically just like an identity sort of. Whenever you have something like this, you get 2 pi just naturally. So 2 pi, and I'm just going to go back up to my square, wherever I put my I squared. I'm just gonna put 2 pi outside of it. Just gonna put that right there, just so I remember. Okay, so now going on to a different color, I'm left with 0 to infinity of e to the negative r squared times r dr. Um, I mean, like, the reason that this works is because it's essentially just this and then theta. It's this is going to just act as 1 essentially, and you're just going to be able to cancel them out, and it's just going to be 2 pi minus 0, which is 2 pi. So this is kind of the long haul, and this is where you can start implementing stuff like U substitution. Okay, so here, knowing that there's an r squared up here, if you've been following this r squared, I changed the r squared obviously from x squared plus y squared into polar coordinates. So since it's r squared and it's the highest degree, I know that this basically has to be my u. And I'm not going to keep it negative, mainly because, okay, pen, I know how to integrate e to the negative u. And I mean, you could keep the negative, but make sure that you would put a negative outside the integral. So, and then 2r dr knowing that I have r, I'm just going to rewrite this. I only have r, not 2r. I'm just going to put a 1/2 out in the front. Because this is essentially, you know, basic u substitution, dr over 2 equals r dr, basically. Um, so 0 to infinity of e to the negative u times du. Okay? And here we go with just basic integration. Go 1/2 times, what's this? E to the negative u is just negative e to the negative u, and then plus c, but it's definite, so to that, which is just going to equal, you know, 1, because negative e to negative infinity approaches 0, and then e, because this is e over infinity, which is 0, and then e to the 0, which is 1, negative 1, my bad, but it's 0 minus minus 1. You see? So it's just 1. So that's what this approaches, so it's 1/2 times 1, which is just 1/2. Hello? Can I not be stupid today? There, 1/2. So this part of the integral, let me scroll back up, was equal to 1/2. So if you remember, what we did was we changed the two integral. We made this so the integrals are multiplied here. So this part with this, well, not this part. Let me go over to the next one. Oh, my bad. This part over here, this was 2 pi. The 0 to 2 pi ended up being 2 pi, and then 0 to infinity was 1/2. And since they're multiplied, we're just going to multiply the products, but we're just going to multiply what we got from both integrals. So we got pi. So we got I squared. The integral of this entire thing squared equals pi. Pi over 2, my bad. Oh no, just pi. So, you know, to get the actual integral, which was just I, to just get what I equaled, we're just going to square root pi. This is your answer. Square root of pi is your answer. Let me just rewrite this entire thing so you can see. Square root of pi. Basically, these sorts of integrals suck because there's so much work, and you know they're often really, really just, you know, just tedious. But there's also a trick that will help you know these types of integrals. Literally, like if you can understand this trick, it will just help you right off the top of your head. You won't even have to think about it. Okay, let me just rewrite um just the integral, but in like basically just a not e, just a normal form. Okay, e, that checks out, to the alpha. Oh, not that. X squared dx. This equals, every time, depending on what alpha is, it equals pi over whatever alpha is to the 1/2. Every time. So let's say I have e to the 3x squared, negative 3x, and it's evaluated from these boundaries, infinity or negative infinity to infinity. My answer is just pi over negative 3 1/2 every time. Stuff like that. So thanks for watching. Hope this helped.